but I do want to spend at least 10 minutes on differential equations, because that is the new syllabus component. A lot of this stuff can be found in a lot of old resources. So so far in mathematics, we're only dealing with algebraic equations. These are equations of the form, px equals 0, for example, x squared minus 5x plus x. If one or more numbers satisfy the equation, they are said to be solutions to the given day equation. Find the solutions to the above algebraic equations. So you could use the quadratic formula, and you could see that there's, there's solutions. On the other hand, differential equation is an equation that relates one or more functions to their derivatives. The solution to a differential equation is a function. That is, if a function y of x satisfies the differential equation, then it is a solution. Generally, differential equations have an infinite number of solutions. So it's basically saying that there isn't one answer to a differential equation often, but instead the answer is actually a function, and that function has multiple answers. You could sub in any answers to satisfy that function. So we're going to go through some of that. So here's an example of a differential equation. We have y dash, or dy dx, is equal to y minus x. The solution to this differential equation is any function whose derivative is exactly equal to y minus x. So there's actually many answers. Here's one of them, right? Show that e to the x plus 1 is a solution to the above equation. So we just differentiate it, we find dy dx. So we can see we've done that. And e to the x plus 1 is actually the same thing as y minus x, because this is y, and then if you subtract x, we can actually see it's e to the x plus 1. So the derivative of this happens to also be y minus x. Hence, because that solution worked, it's an answer and it satisfies the differential equation. You can see there's multiple answers. We can even try 21 e to the x plus 1 is also a solution. So again, we differentiate, we do y minus x, and we can see it's actually the same thing. It gives us the same thing. Derivative is 21 e to the x plus 1. Y minus x is equal to 21 e to the x plus 1. So that means they both must be equal. So this is an equation, this is a solution, and this is also a solution to that differential equation. In fact, if you put any number in there, if you put a in there, it will actually be a general solution to that differential equation. This is called a general equation. To obtain specific solutions, we need to evaluate a using a point on the curve. So we actually need to pick a point to figure out, what if you want a specific answer. As rates of change are very common, differential equations are extremely important in many fields of engineering, physics, economics, and biology. For example, population growth can be modeled by the logistic equation. So this is population growth. If you remember back to exponential growth and decay, in a lot of these scenarios, we actually have these differential equations that come up, especially in engineering. Another example would be the area equation, which isn't really in the syllabus, so I'm not going to go into it. It's actually a second order differential equation, and this is actually what they use to work out the curvature of rainbows. So that's kind of cool. There's so many differential equations, and when you guys start university, you'll spend your first year learning differential equations, and it's going to get messy. So I'm glad that you guys are practicing basic ones now. So firstly, let's try and pick out which ones the differential equations are. So we guys can do this together. Which one is the differential equation in this case? Where is it? Yeah. Which one's the differential equations? A, B, C, D, or E? Identify the differential equation. It's going to be things that have derivatives in them. So A does not have any derivatives, so no, it's not a differential equation. B does, it has y dash. C does, that's that 5 there, that means a fifth derivative. D does, it has double dash in there, it's a derivative. 2E does not. Differential equations have orders as well. The order means what number derivative do they go up to. So this one is the first derivative. It's a first order differential equation. This one is a second order differential equation. There's a double dash in there. This is the nth order differential equation. You have an nth order differential equation in there. Cool. So verify that this is a solution to the differential equation. That it's quite easy to do. You just find y dash, find y double dash, and sub it into these. Sub it into this and prove that it's equal to 0, starting from the left-hand side, ending up with the right-hand side, and you can see if it works, then it is a solution. So those type of questions are quite easy. It is known that y equals e to the alpha x is the particular solution to the differential equation. This, find the possible values of alpha. So again, we sub it in. E to the alpha x, you differentiate it once, differentiate it twice. Now sub it back in. Now it has to equal to 0. We can actually factorize out e to the alpha x. It's common in all of them, which means the alpha comes out. We end up with a squared minus 5a plus 6, and we can factorize it to find a. To solve this differential equations, we make y dash the subject. Y dash equals to 2x. The integral of y dash equals 2x is going to be just x squared plus c. So that one's actually quite simple. Then we have slope fields. So we've learned that there are an infinite number of solutions to a differential equation. If a function satisfies the equation, then it is also a solution. We can represent all of these solutions on a Cartesian equation. However, sketching all these curves on a single plane is impractical. Like, there's so many solutions, you don't want to sketch all of them. So instead of sketching all of them, you can actually use small dashes indicating the gradient of a solution for many equally spaced xy coordinates. This is called a slope field or a directional field. To construct a slope field for a given differential equation, decide on a domain and range to plot the slope field and then a step size. Calculate the value of the derivative of each of these points of the required points. At each of the required points, draw a line that shows the gradient at that point. If we are given a point that lies on a solution, we can use the slope field to plot a particular solution containing that point. So we're going to go through that right now. So let's look at the differential equation y dash equals to y minus x. We can use this equation to calculate the derivative at xy coordinates. So let's find y dash at the xy coordinates 2, 2. So you sub in 2, you can see y dash is actually equal to 0. So we draw a horizontal line at 2, 2. Repeat it again, for 3, 2, and then again at multiple different locations. And if you do this, you draw a little line, a tiny little line. 0 means a flat line. -1 means you draw a tiny little line pointing -1. So if you actually look at 3, 2, so 3, 2 is right here. So 3, 2, you can see they've drawn a line that looks approximately like -1 there. And at 2, 2, they've drawn a line that's 0. So 2, 2 is here. You can see that it's 0 there. The gradient is 0 of that line. So you can see you end up with this cool shape. It looks like somebody's run their fingers through the water, kind of like if this was water, kind of interesting shape. Using the slope field, we can sketch a particular solution passing through a given point of the following line. So now we can actually sketch solutions. So to sketch a solution, we need to pick a point. So let's say 1, 1. So what we do is we get 1, 1, which is here, and we kind of just follow the lines if we were to follow follow those arrows. So you can see it kind of goes along this way, goes down, curves down, goes straight down here, and it actually kind of curves up a little bit across like this. So we can actually draw that, and we can see a particular solution that goes through 1, 1 looks like this green line over here. So that's how you can use slope fields. So let's go through an example. Draw a direction field of dy dx equals to x between 3 and 3, x equals 3 and 3, and y equals -3 and 3 in increments of 1. Then sketch the solution passing through the point 1, 0. So we've decided the domain and range already. It's given in the question, and the step size, which is 1. Now you basically just use a table of values. The x coordinate is at the top, and the y coordinate is at the is on the left here. And we want the dy dx is equal to x. So all we have to do is fill in this table and write down what the gradient is. So the gradient is actually just equal to the value at the top of the table because it's just equal to x, and these are our x values up here. So this entire column is -3, this column is -2, this column is -1, and so on. Once we do that, we can actually use these as coordinates and draw a line corresponding to this gradient in red. So we can see that we end up with something like this. At 0 we have 0, and then at -3 and 3 you can see it gets steeper. Use this slope to find and sketch a curve passing through 0, 1. So sorry, 1, 0. So we go to 1 and 0, and we can see that goes through here. So now we need to sketch a line that goes through here. So it's probably gonna, if we continue this line, it'll touch this. Continue it, probably go up here. So we're looking at something like this, and then it'll come down, flatten out a little bit, and looks like it's actually curving back up. Almost looks like a parabola actually. Kind of curves back up, something like that. Oh, the answer isn't here. Use a slope to sketch the curve that passes through 1, 0. But yeah, you get the idea. You essentially kind of like join the lines, and it ends up drawing a solution for you. Draws a solution for you. Cool. All right. Draw the direction field for the equation y dash equals to x minus y over x. So again, you just do the exact same method. Plot a table. The table values will just follow this simple formula, and you end up with something a bit crazy looking like this. Now, it's probably unlikely that they're going to make you draw one of these in the HSC because of how long it takes to draw. But what you do need to be able to do is be able to recognize them, or if they gave you one of these, you should be able to draw this solution, the particular solution that goes through a particular point. So we have y dash is equal to x over 1 plus y squared, shown here. Sketch the solution to the curve of the differential equation corresponding to the condition y minus 1 is equal to 1. Okay, so y minus 1, that means an x value of minus 1 is equal to 1, so that's going to go through this point here. So just join the lines. You can see it's going to curve up like this, flatten out, and then kind of curve down like that. So you can actually see that solution there. There you go, looks something like that. Then it also asks you estimate the y-intercept. So you can give an estimation of the y-intercept as you do that. And it kind of looks like it goes through this one at 0.9, or 1.9. Cool. Sketch the slope field of differential equation for, this could be a typical exam question. You can actually, they give you the grid and ask you to sketch it. So you want to sketch it at these points. You just sub in the values, do mini gradients, and sketch the solution. There you go. You can do long lines if you don't have many points. You don't want the lines to touch, but you want them to be somewhat close together because it really depends on the step that you use, and the step that we're using is quite large. It's 1. So we can see when we join them, it makes a curve like this because we want to pass through 0 and minus 1. So that's that point there. Cool, so match the slope fields with their differential equations. You want to practice this. So you're probably thinking like, how are we supposed to convert this field into this point? And it's actually, you do the reverse. What you want to do is you actually want to use this and, what am I trying to say? You want to use this and sub in some values, and see what it starts to look like. There's actually a really good, if you just Google slope fields, there's a really awesome video that explains how it works. I think it might be a Khan Academy one. I was watching one the other day. That was weird. Not creating a slope field. Where's my history? I think it's this one. This is the one. Organic chemistry. So it's kind of near the end where it's quite useful.
And if you plug in 0 for
so you really just sub in numbers. Let's see. Here we go.
And see if that point works for each equation. So let's focus on this point.
So this shape looks quite similar to D.
X is 0, y is 1, and the slope, notice that we have...
So you just pick a point. So what you picked was x equals to 0 and y is equal to 1. So in D, you just pick a point. So we pick this point here, and we can see that the gradient is 0. So we can write, at x equals to 0 and y is equal to 1, the gradient is 0. So now you have these set of points. You have these 3 sets of points that you know, and you just sub it into any of the equations that you have. So when we sub it into the equations in the question, it will actually tell us. So I guess the trick with this is make sure you choose points that are different. On the same point, the gradient is actually different. So 0, 1 would actually be a great example, because 0, 1, you can see it's a positive gradient there, it's a negative gradient there, it's a flat gradient there, and I guess for this one it would be kind of dangerous to mix A and C together because they have that kind of similar gradients. But essentially, you just pick a point and you test it in these equations that they've given us, A, B, C, or D, and see which one it actually works for. And when you do that, you can actually see that it doesn't work. So I guess I'll link you guys this. It's kind of the extended version if you want to know how a slope field works. But I thought it was quite a useful, a nice one there. So we end up with A ends up being B. So we can I'll show you an example real quick. So I like picking a flat one. So we can see here at well, we can even pick 0, 0. We can clearly see that gradient there is -1. So y dash is -1 and at 0, 0. So we sub in 0, 0. So sub in 0 here, you end up with -1 and y dash is -1. So you can very quickly see that this one satisfies B immediately at 0, 0. Picking the point 0, 1, 1, 0, and 0, 0 are obviously the easiest because you have less work to do, you have less to sub in. But there are scenarios where it wouldn't work, right? Or not necessarily wouldn't work, but if you subbed in y equals to 0 in this scenario, you get something divided by 0, which actually makes a vertical line or a vertical tangent. So if you ever see any vertical lines, that's when you know you're dividing by 0. So you can see there's some vertical lines probably on this end or kind of around this side. It approaches vertical lines. Cool. Solving differential equations. This is the last section of differential equations and by separation of variables. Now, separation of variables is actually very simple. It's just separate all the x's on one side and all the y's on the other side. So if dy dx is equal to f of x to g of y, then put the g of y down here and put the dx up there, like so. And then integrate both sides. Cool. So in this case, we have dy dx equals to 6y squared x. Just put the 6y squared at the bottom. You can even leave the 6 there. 6 is a constant. It doesn't matter which side it's on. You can put the y squared at the bottom here and the dx at the top, and then you just integrate both sides. So we can see we separated the two variables. Integrate y squared. 1 over y squared, and then integrate 6x as well. And you can see the values become quite easy. They should give you some initial conditions so that you can figure out what that plus c is. Yeah, there you go. Y1 is equal to 1 over 25. So you sub that in, you can work out c. Otherwise, what you can do is, if it's definite integrals, you can use initial conditions to work out an equation. So what I mean by that is this kind of comes up in a little bit of mechanics, sometimes in temperature and things like that. But let's just use I don't know if they have indefinite examples in here. It doesn't look like you do. But let's just use this as an example. So we have separate the variables. Dy over y squared equals to 1 plus x squared dx. Integrate both sides. Now they've given us initial conditions. They says when x equals 0, y is equal to 1. So when x equals 0, y is equal to 1. Now we don't actually cover this but in this booklet, but there's a really cool thing you can do is you can actually, as long as they correspond to each other, you can join them up on the same level. So we can actually put, this is the x side, so we say x equals 0, y is actually equal to 1. This is a shortcut for not having to find c. When you put 1 there and put 0 there, that will automatically find c for you by converting this into an indefinite integral. We don't have any other initial conditions, so what we can do is just call this x and call this y. That will just, just give us the variables. So Check with your teacher before if they're happy with you doing that in school, but in the HSC, they do accept this method if you put your initial conditions at the bottom there. So that's totally fine. That will save you, you know, having to figure out C. Yeah. But I think that's pretty straightforward. Because once you've converted into this, then it becomes just normal integration. You just have to integrate both sides of the equal sign at the same time. Alright, and then there's some more practice questions that you guys can practice. You can let me know if you have any questions later on. But yes, thank you so much. We kind of went over time by a couple minutes, so that's not too bad. We did manage to finish the majority of this booklet.